YouTube is now live as well. Hello Amaboyd, hello Deshipu, hello Electron Ash. We are live and I should hear you. I don't see it. Don't hear it yet, but it should be there. I don't know. This one isn't. Doesn't speak. TTS. It should play TTS. Hello, Izutsumi. So last time, I'm wondering why we don't hear it this time again. It should be alright. Where is it? We debug it shortly. It's every single time we get the same. Ah, now it's working. Okay, I can hear it now. I don't know why it took so long to. Hey everyone. So last time we performed some tests, even with frequency analysis on what we recorded, and I worked a little bit. Birds, yes. They're quite active. So I tested how it would look like. This is like what is it, 100, almost 100 hertz. Yeah, frequency 100 samples per second. Where is it? Oh wait, this is the wrong. Here is the code. Encode byte. I only, so when I try one frequency, so we have like 9 carrier frequencies that we wanted to encode, which was looking all right on the FFT for like 20 bytes a second, which apparently is a terrible data density for tape. And now I'm doing, oh yeah, 100 bytes a second, which, or it's at least 100 samples. If I look at the DFT, so I encoded, where is it, my test? Oh yeah, decode ADC. So I'm only decoding one frequency and testing how it looks like. Okay, the test runs and encodes. These are real birds from my garden. No background audio. That's. Hey Eddie. I am living quite remotely, so you could even watch them. So I tried like encoding 1 bit and then 3 bits at most. It's 8 o'clock here. And what yeah, this is like running a DFT on just one frequency right now. Wait, this is wrong. Decode ADC. No, that's right. The frequency that I pass, and what it does, it sums up the samples multiplied by cosine and sine for the window size, which is exactly one wavelength of that frequency. That should change if we do it like simultaneously for all the frequencies, so we can't like have the window be exactly for that frequency. Oh, see you later, Annaboy. Hey Peter, greetings to Boulder, Colorado. Yeah, probably not next week. I don't know when I will be back from the trip. So maybe I'll keep you updated on, I don't know. Oh, on Twitch it's can I put a message on Twitch? Probably not. Catch some time. No, it will be raining from Monday. That's terrible. I checked the weather. Discord. Yeah, I can. Yeah, I will put a message on Discord. That should be doable. Unless I'm dead. So I tried like to run a DFT on the one of the carrier frequencies, and this is how it looked like if I store like 100 bits. It is good for the dead. 100 bits, like each of those is recognizable. It's quite good, a nice density. But then if I use like 3 wavelengths at the same time, yeah, there is the response you couldn't decode. I'm decoding one frequency here, and this is what the output would be like. Then I can wait, retest, let's run it. And yeah, this is basically what I get return. So we can't use that as compression method. If I would like change the density, busy signal of the phone, yeah, but not in Germany. Discord. All right, so wait, this is the wrong code here. I was debugging. If we try, let me do not 50. Let's do like, let's say 100, and we do 50 milliseconds per sample, and code that. Modern refinement. It didn't rewind. I was wondering why. Okay, rec test. It's now storing the data, and why didn't it rewind? Strange. I added the rewind to it, but it wouldn't. Okay, now let's do the retest. Now you can hear it, but still you get the response isn't perfect. I don't know. It's if the frequency is off, I couldn't tell, or we can run a test, change basically the frequency. Well, let me check what our distance between the frequencies is. So maybe we just need to tune it a little bit more. Okay, so we have somewhat like 60 hertz separation only between those channels. So I'm wondering if we try like decoding. Wait. Carrier frequency. Okay. Let's try decoding different frequencies like plus 10 plus 20. Oh, we should do minus 10 minus 20 and then see what's the best response. And we do only 400, so we can see hopefully, oh yeah, sample buffer, oops, 400, and this will be the address. Or can we do sample buffer plus? Okay. Let's leave it. We can try decoding different frequencies here. I'm wondering if that has to do with something, with anything. We should see 1/4. Okay, this is okay. Now retest. Where's my response? Why wouldn't it show? It didn't update, did it? No. Here we go. All right. I don't see a difference here. The frequency response is basically the same. Huh? The separation is only like, there should be some difference. I'm doing something wrong. Let me check. Let me see if I see an error here. Maybe that my DFT is crap. interesting here. We get more interference. It's getting smaller. What is going on? It doesn't look like there is any change to that. It's like the amplitude of all the frequencies. Are they just too close to each other? Huh. I would really love to see that working. Okay, let's try again. This is 1600. Oops. Let's do 0, the lowest frequency. And what we can do here while encoding, where's the encoding? Bytes, decode, encode byte. Yes. Oh, that's only 2 frequencies. Wait. Did I decode 3? There was no 3. Which one did I decode? Yeah. That was the wrong frequency. Ah. Okay. Let's try again. And start with the 2 frequencies that are actually present. There should be a massive response. 0 and 1. Is this some kind of meme, the Shipu? If yes, I don't know that one. Oh yeah, upload it first. Ah, title of a song. Ah. Okay, let's start and Rita. No, doesn't do anything here. Also, why is it dividing by 4 if we have only 2 frequencies? We can have more. Bloop, 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 bloop. Yeah. It's running the test. It's running the test. Oh, it made it. The rewind. Okay, now. Huh? I don't see a difference. It did update. I uploaded it. Let me try. Wait. Carrier frequency. Let's do carrier frequency times 4. Here the index, so we have bigger separation, and then we should see nothing on the second one. The waveform updated. Right, this is the code. Need to check that there is no error. Frequency. Yeah. We updated, did we? Yes, we did. Okay, I reload so you can see that there actually is a change. Rec test. And then read test. Oh, this is interesting. We see but I'm wondering why this part is like so long while this one this is testing another frequency. It doesn't work. Let me see what the implementation of the FFT is. It looked like the FFT is doing a better job. Spectrum. Float array. Waveform diff. What do you mean? FSK? What is FSK? Frequency shift keying. Is this what the data set was using? Yeah, it looks like that. We can do this like what C64 was using. Oh no, too much work. Don't do that. We can also show. Oh wait, let's go. Let's do 4. Let's test the actual frequency, like the high frequency. I wanted to store more bits per stream than just one, but the way like the dataset worked is quite interesting. I mean that is FSK basically. It just uses a Schmidt trigger, which counts the 0 passes through of the waveform. So we have like this level, and then if it's only like 1, 2, so one complete wave, then it's a 1, and if we have like more, double the frequency, then it's a 0. So this is if we like use a high frequency there, I think we were able like 4 kilohertz was alright. So you can imagine we can store 2000 bits per second. And if that works, and then you need like CRC and additional bits and whatnot to test that. Oh, by the way, I got a broken device today that I bought off eBay for parts. People will kill me that I take this piece of history and take it apart, but you can't even press the record button. I don't know, it seems blocked or something. And I wanted only the record head. Maybe there is a stepper motor inside. We can take it apart if you want to. .4 centimeter. Oh, there is rewind and fast forward. Oh, that feels like it was probably taken apart already. It will not have like this one. This one has one. This is a stepper motor, and I wasn't able to find flat and small ones like this. I wanted to get, but that's already quite wide. I ordered the stepper motor that would fit because I don't want like any gearing whatsoever. If I build this drive, focus, and it will never focus. Oops. Go on, focus. Oh, what? Oh, what? You're kidding me. Not on this one. There are no right protect. Ah! There is no... Oh, wait. It looks like there is something. Oh, yes. Here is the tab. There is one on the side. Interesting. Okay, I got some tapes with that, so let's see if that works. But I think it wasn't working. At least it was sold as broken. I paid only 15 bucks or something. So where are the tapes? I got even like 2 tapes, and if you pay the tape, buy the tapes new, you're almost at the same price. Or the 60 minutes. Here, no, that's the DV tape. Can't find it. My lab needs some cleaning again. Huh? This is really strange. Got two tapes. Ah, there I are. They're so small, can find. Yeah. Okay, let's put it in. Oh, now it works. Okay. That looks actually really cool. But it looks really cheap as well. Oh, there are even like two potties to tune something. Hey, Jolly. More processing, you could do 4 frequencies and get 2 bits per symbol. Would you do the decoding or encoding then? Curious. I mean, we tried. We should start with the cheap ass method, encoding bits. Should we just and try to do what is this frequency FSK? Did the Skidiki pop pop. Frequency shift keying. How do you find the start of a symbol in FSK? Does anyone know? Let me start doing it. So on this screen only not much fits. No, I didn't. I thought we can do some cool processing here, but it seems that my processing doesn't work. Casper, maybe you're good with audio. Maybe someone finds an error with my decoding technique. So what I'm doing right now is I'm calculating. Basically, I have a window of one wavelength, more or less, and I sum up the samples. So let me do it here. So it's basically sum of basically all the samples. So sample times phase, yeah, it did it right, divided by n samples. So this is amp s. I do this, then I do this, and then this is basically what I do right now, and this is then the value that I return. I don't pull like the square root from that. Square root would make the difference even smaller between the ones that are. I don't know what's missing here. This is the value that we get. Ask from AI? No. Why? Okay, let's ask AI then. But that was working before. Wait, where's my ChatGPT window? If it gets anything better, if you're not ready, here. I do a new chat window. Okay, I asked it to it's doing FFT, but I don't want a FFT. Wait, analyzer. Start oscillator, wait. Analyzer. What is the analyzer? Huh? Audio constant. Hey Nicolas, I'm currently, I don't know how it's called, just modulating, like adding different frequencies that I turn off, on and off, and then I try to decode them, but it feels like I have an error there because I get a response from more than one frequency right now. The separation isn't that great. I don't know why. Yes. It's probably not that great. But digital, I mean the amplitude is either 1 or 0. Goertzel. Target frequency. Okay. Math round type K. Sine. Oh, that looks interesting. Hey Quindo, what? Phase shift keying will probably not work because the playback speed might not be constant. So there is also, we have some frequency shifts anyways, and probably some phase shifts as well. I have no clue. Okay, Goertzel. Let's read. It's probably, so what Goertzel algorithm is doing, it's just multiplying the peaks of cosine and sine functions. As I can see from the code, is it? Cos, cosine, omega, sine, omega. Wait. Why does it calculate? Okay, so sample rate, target frequency, and signal length. Hey, foo! Is this for the... Thank you very much for the super chat. Is this meant for the excavator or for beer? Two times cosine. What? Yeah, I put it in the excavator fund. Thank you very much. Me too. Excavator fund. Here. Bam. Thank you very much. Signal I plus coefficient time. What? Is this some infinite response filter? Previous two, yeah, this looks like an IRR or something. Cosine. Oh, magnitude. Yeah, there's the square root. This is strange. We can test it though. Give me... Ah! No! Give me food! I copy-pasted the wrong. Goertzel. C++. And fixed point math. Don't use score at the end. The square is good enough. Double. We should translate it ourselves. Don't square root at the end. Dudes, please behave. Okay, let's do it. Let's translate it ourselves, okay? Goertzel filter. Okay, decode ADC, let's do it. But we don't have the actual size. We can set a sample rate. Oof. Okay. Signal will be stored. We have no signal sample rate. We have target frequency. Okay, so. And then we have, it's basically the same like here. Signal length, yeah, that will be, we should, let's just, oh, it's calculating on the fly as well. Coefficients and then the magnitude. So we are performing also a moving window test here. For you can, isn't it open source? It's just an ESP, I think. Isn't Stuka 0 just an ESP32? You just need to get the firmware on that and you can run it anywhere. Or is there like a software defined radio on that? Not sure. Hello Z80. Imagine, yeah. I missed your hello. Yeah, we wanted to store a file system, but now we are trying different encoding and decoding first. So what sample rate do we do? We can do specific sample rate that's convenient for us, or do we do like 20 kilohertz? So basically 20 kilohertz. Then frequency. Then we have a window. What is K in that case? Times. Okay, that's basically samples versus sample rate times frequency. That's the count of waves in our, and then the round is basically plus 1. It's rounding up. So K is, let's keep K I don't get this. Okay, I need to see what it is Goertzel actually doing. Does discrete Fourier transform? Set application size, blah blah blah. 58. Digital filter. This reason the algorithm is often called as a Goertzel filter. The filter operates in input sequence, cascade, 2 stages. Okay. Yeah. It's the intermediate sequence. Oh wow, that's complicated. I don't want like this implementation. You know what? I will ask it to. I will do the. Or single precision, anyways. Float. or power return to the array pointer that is given in the function params. The function stops when size is reached, and then appropriate window size might be the count of samples per wave. I don't know. Let's see. Streaming Goertzel based power calculator. Can close that. Okay, let's see. Goertzel bin index. Oh yeah, that's the binning then. Wait. K. And omega. I mean, this stuff can be pre-calculated. This stuff is running on the fly. Power. Oh, 600? That sounds great. Oh, thank you for the follow. Who was that? I missed that. Missed the name. Here. Systech. Skytech. Okay, thank you. Yeah, let's try that. So Caspar, what would be your approach? Streaming powers. Okay, here we go. Include math. See math. Target frequency. Yeah, bought like B. Give me some hints. Sample rate. Oh, why is it float? Wow. We can do this. It's sample rate. Because I mean, we can do this. Yeah, let's keep it integer. Float output. Let's size sample rate. Okay. I don't know, because I told ChatGPT to do so. Omega. Sine, cosine. F. Okay. Now it starts. No. I don't understand the 80 code. Wait. Can we even manage to do so? Oh wait, we have enough computational power here. 1000, it should be all right. Oh, it's accumulating. Yeah, accumulating the samples here. So what we are doing is we leave it float and we see if we can even sample at this rate. Yeah, I have a sinus table. Okay, Caspar, that's basically what the dataset encoding is. Here, this one here. But they do like they measure the basically. Yeah, that's we can do that. This is probably the safest, the simplest method. But I'm curious about this Goertzel method, and I hope we can make it work. It's too much input for me. Next sample. Okay, so now I need to implement that. So we have basically sample will be here. Oh wait. Here is the starting time. Then we have come on. DT is basically sample rate, and then that's DT. T is T0. Let's do it. Or let's do DT. That's okay. DT. So now we while get time is shorter than to do nothing. Time, and then otherwise now we do next sample, which is basically this here. and T dt sample can convert it later. Where's the previous? Why is it? It's here. It's here. Huh? What is it complaining about? And what's the window? Why is it complain? Is there like a parenthesis that we didn't close? Schemes, let me check that. Oh wow, this is, I would need like to give you a platform to implement something and then test it. Why is this complaining? I think something's off here. Anyway, oh yeah, we need to change that power basically to F, and then that's it. I can't analyze that right now. That will be... Oh, okay. Here. Yeah, I know. Hey, Chabiota. We're trying to decode bits stored in a specific frequency on the fly, which is running on this mini cassette recorder. It's very tiny, with this tiny cassette here, and we are trying to do something similar to dataset from C64 back then. But different encoding techniques, and I'm trying to explore those. Decode ADC 2. Yeah. Do you still have like a data set at home? You can interface that with the FPGA. It's described actually in here. Everything in the Wikipedia is almost a complete description. There's like this connector that would work with a regular PCB. Edge connector. If I close my window, no. All right, decode frequency. Let's try. Oops. My decoding. Okay, sample buffer. 10K. Is this all right? We can do 16. Oh, wait. This will be probably a long time. 900. Why do you doubt that? Because of the rubber thingy that rips apart? Huh? Okay. Let's try to compile it. Alright. Expected expression. What is it? Huh? Huh? Are you seeing what's wrong here? Wait, CMath, maybe there's the includes. Why though? Huh? Here's everything that's... Huh? Here. That's the issue. So silly. Okay. Let's run it. Is it rewound? Retest. Oh, it actually responds, and I think this is just an overflow. Let me do it. Let me, since it's an addition, wait, decode ADC, power, yeah, we have, okay. If that method would work better than what I implemented, I'm upset. Goertzel was smarter than me. Huh? Still? Did I update it? Oh, wait. Still. All right. Maybe it's very responsive here. The Goertzel test. Or the encoding is bleeding into the other frequencies. There is something that I need to admit. I did something. No. No. Peeps. Sample rate frequency. I can set it whatever I want. We are currently at 10 kilohertz for a signal that's under 1 kilohertz. So Nyquist is 2 kilohertz sampling rate, but we are above that. We could do higher but I doubt that will fix it though. So let's try. Might be my encoding might be bad. Yeah, let's do 20 kilohertz. That should be doable. I don't know how much the float emulation is taking, but we have 1,000 cycles per sample. No, more than that, 5,000. No. Yeah, that should be still enough. Okay. Oh. Let's wait for it to rewind. That is a different frequency. Performs even worse. Quantify the amount of noise. We had a good response. I can't. Wait, okay, you know what? I'd show you something that you might want to see. Okay, here you go. No. Okay, this is from last time. Yeah, we are past this. Here. We have a good frequency response. You can see the bits here. Okay, there is some noise around it, but the song that we encoded last time here. This is 9 frequencies at the same time. And you can see here individual bits which were I don't know. Here, this is old stuff. But this is old news. Looks cooler than what we are doing, but this was just visualizing. If we can see with our naked eyes if there is something there. So what's interesting here that the lower frequency no, stop it. Yeah. But this is old news. I want to decode now, not the past. Stored data as PowerPoint slides. I recorded it on the camera. So oh yeah, this is not good. Oh, stop that. I could I could export some of the data to a file, or I don't know, to a header file or whatever, and analyze it not on the microcontroller but like in the browser, which is way faster, and then see what's the best decoding method. But the problem that I also got with the encoding, we can't use like the DAG isn't perfect, and also the range is only that we can use of the 8-bit DAG is only a range of 32 different values. We have a sign table that we squeeze in that range, but like with only 5 bits of precision, that is quite noisy in the end. So there is a lot of square wave features that are reflected in the other frequencies. There's the thing that I needed to admit to you is basically that yesterday I sat down, and since we currently are using for all the control and so on, this is just an old project from mine, from a matrix board with which we like botched on the interface to the recorder there, which, if you didn't see it, is like there is the tape, and that's like an unfolded best setting vibe code spectrogram. I asked for all the settings to be adjustable with keyboard shortcuts so I can search for it. I say, interesting, okay. Yeah, so the problem that I got is like the range of the voltage range. KiCad, the windows are resized automatically, so it wouldn't fit the screen anymore. Thank you, KiCad, for nothing. Here, I sat down and what's happening is let me paint it. We have a voltage range on our recorder which is no filtering on the DAC output. So except for the writing head and the tape itself, 1.8 volts is our tape, and the wave that's stored is not even like around here. It's like this area, and then anything higher will be clipped because there are op amps that are not going up to 1.8 and clip below as well. So there is some loss, and we are at 3.3 volts here with our microcontroller, and we have our range from here to here, which is 255 or 256. Okay, this is a 256 values. So this usable range here for the tape is quite small on that scale. It's around 32 plus minus 16. Yes, so already quite crappy. And if you superimpose multiple frequencies on that, yeah, that's tragic. But I'm not new to this game, maybe to the analog game, but not really to the DACs. So I ordered a new PCB yesterday. We have either two 8-bit DACs or one 16-bit DAC, which is buffered at the end and can be adjusted to the specific voltage range here on the output and on the input as well. Yes, this is what we are doing here. So using that we can basically no, this is the input. Wait, are we making it smaller this way? No, we double it with that. Pulling down. Yes, this is halving already the voltage. Yeah, anyways, it's buffering here. We have like the option to put a capacitor on there, to put it somewhere like, I don't know, analog voltage. We can also operate on 5 volts on the op amps, not only VCC. And yeah, we can do 2 DACs if we use the board for stereo, which is not possible on this small tape, but whatever, we can do even 2 DACs, like 8 bits. And then also another op amp for the input, since the input range suffers from the same problem. We can double here like that. First of all, there is like a voltage shift because now I'm taking the signal after the amplifier of the recorder. So this is the signal that goes to the speaker, but we can pick up the signal before even like the volume knob, which is analog. So with that thing we will push it, bias it to the center of our VCC and then amplify it even more. The ADC is 12 bits, so we get quite a good adjusted. The boards are ordered. You want the filter before the op amp, you think? What filter? We can put anything here. Capacitor, yeah, I could here. There is already a capacitor. On the DAC side, here, you can put a capacitor there. On the DAC side, oh yeah, can we do something? Yeah, we can do like a low pass filter, while putting here a capacitor and here a resistor. Wait, no, here. No, here. Yes. I think this, yeah, capacitor and resistor, that will be input side of the op amp. Yeah. What do you want there? Dusty. What should we put there? I mean, this is what we do now to half the voltage. The filter, what does it do? How does it look like, the filter? Low pass? A low pass filter. What we can do is we can put a capacitor here. Does it matter if it's charged between VCC and ground? It doesn't matter. So we have like 10K here, and we can just put a. Do we need YG&D? We can. The low pass can be also VCC. At the the signal here is centered around half VCC. So it's the same distance to ground as to VCC. So our virtual zero is around half VCC. So it doesn't matter if we have a cap towards ground or VCC in that case. And the current is limited by the 10K here already. So we can put here a little. Ah, all right. Okay, I see that. Yeah, didn't foresee another space here for thing. But the boards are already ordered, and I can't change anything about that. Otherwise, they won't be in time for until I need to finish my video. So yeah, so interesting. What? Yeah, I can put it on top of the resistor. Yeah, it's not the first time I would do something like that. What is that? Huh? Wait a second. What is this? What? And also, what is this? Huh? Okay, I'll show you what it all means here. There's not much happening. Okay, show me the PCB. It loads. It's very slow. Ugh. You will hate it. There is no mounting holes. Okay, let me remove that. Here. We have a proto board like with extra 16 GPIOs to do whatever we want. And yeah, this is the interface for the buttons. This is power for the DC to DC converter. This is the ADC stage. Here the ADC, and this is the DAC with the buffers. And interesting part about that, I have the output of the ADC. I can either connect directly to the ADC, or I can connect through the op-amp. So there is this option, the same for the DAC. I can basically not use the op-amp stage for the DAC. So if you say, oh, we need a series filter, I could take this signal and put just a new dip op-amp here and put the filter here, like root, take the signal, take it here, make the filtering, whatever, put another op-amp on here and make a new output stage. Yeah, so and this is basically, I just measured what would fit between like a sandwich here. So this is 5 centimeters by 4 or something, 4.5 centimeters. So it will be sandwiched in between here, and it has a USB. I'm curious how this will turn out. It would be funny. But what I wanted to say with that is that we most probably will be able to send a cleaner signal to the tape and receive a cleaner signal from the tape. Hopefully. I don't know. Maybe. We will see when it's ready. Alright, so let's do the encoding then. Why is this? Dremel carnage. Okay, so we want like the encoding, this dataset encoding. Okay, let's do... Where's my code? Where did my code go? Here. The DAG is not log scaled. Chris! You're evil. I know for audio it would be nice to have a log scale DAG, but where do you get the resistor values from? Is there other like any ICs that do like a DAG, log scale DAG? Logarithmic resistor ladder. Let's see. Precision Vishay dips. I mean, we can put the values there, logarithmic values. Oh, I know how we can get the precision. Okay, the logarithmic or quadratic stake, because audio is basically perceived that way. Yeah, so Dremel resistors, or we have a resistor ladder with surface mount resistors, like here, this is R, this is 2R, here, boop, 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 then we have again R, then we have again a 2R, and I think what we could do is we can just stack it, just two on top of each other. So there's another 2R here, stack it, and then we take 4 resistors on top of each other. Yes! 4 resistors on top of each other. These are surface mount resistors. We can stack them endlessly. Tag sandwich, and then boom! This is 2R. And then we have also 4 of those. From an information theory perspective, I think log scale will waste bandwidth. Yeah, probably. So let's try the encoding. The encoding of, what is PSK? Yes, I know. Yeah, that's what I would do. Like stack them on top of each other. It's not the first time I would do that. It's fun. Or tombstoning. There's like this capacity. CD? Oh really? There is a chip for that? It's this. It's a switch. Are you sure it's the right one? Okay. Let's encode bits. Okay, let's encode bit. Yeah. Okay. Times frequency, frequency times 2, done. Encode bit, that's the PSK encoding, but we need to be, is it P, what, PF, no, what's the name again? Encode bit 2 BSK? No, I have no clue. The frequency encode. Okay. Encode bit. Let's take 2 kilohertz. As 2 kilohertz is 500 microseconds to ticks. Okay, so that would either store one wavelength of. Oh, but the wave doesn't start from 0. Yeah. Okay. Anyways, I do the following. Let's decode 256. We can store all the bits here. Almost. What's this? What? Oh, J. Least significant bit first. Okay. So this should be encoding. What is this doing? No. Encoding 256 waves, bits, like, I get it right. Like the C64. Let's see what it generates. And where's my window? Here. We are here. Always want to see that at the same time. Okay. Huh? it's okay. What's going on? 256 times. Oh wait, that would be really fast storing that. Hmm. Should we do it? No, we're not trying to be compatible, Chris. I just want something that's reliable. We have 1,000. Oh yeah, that's done in 1 second if I don't do it like that. That's okay. Now we just do it 10 times. What does bias frequency mean? I just use now 2 kilohertz, which might be too high already, but I try like a higher density here. Okay, let's start it. Huh? That's off. Oh, that get time thingy. Oh, damn it. My fault, peeps. What do you mean? Bit low. On tape? I don't know what bias means. It's like here. What I know is. Wait. Where is it? Here, FSK, frequency. Yes, but it's used for the internal clock. This is this frequency is 2 kilohertz. This one is modulated. Yeah, but it's not the same like the data set. They just double. Yeah, that would be Bell to yeah, that's so 2 kilohertz is, and then 2 and 4 kilohertz is already higher, which I doubt that we can achieve. But we could do. Yeah, let's try with that now that I uploaded. What? But you can't store that on tape, Chris. How do you store that on tape? The response of the tape isn't that great, or of the write head and read head. we wouldn't even see on the oscilloscope. We tried storing frequencies and the amplitude just dropped so low at some point. Oh, you know what? That was on the speaker. So if we detach the speaker and read directly from the head, that might be higher, but I'm not sure. Why is it that, like the tape recordings, why they're so... But that's not an audio cassette, that's like a micro cassette. Oh, really? Can someone look it up for me, or... Audio cassette bias frequency. Okay. 30 and 50 kilohertz. But what is it for micro cassette? Yeah, I'm using 2.4 centimeters right now. So we have actually half the density. So I don't know. Let's test it and see what happens. The issue will be with the decoding though, and I need to... where is it? I lost my window here. Is it rewind or rewound? Okay. Yeah, 10 hertz, 100 hertz to 8 kilohertz. That's what we actually tested. On the spectrogram, you could see like the signal deteriorate at the higher frequencies, and we had like a really low amplitude there, a lot of noise. Let's just listen to... That's what we recorded. Okay. Let's see. Oh, German electrician. That is very helpful. Thank you very much. So we should stay within 1,000 and 2,000 maybe. But what I want to try is... I would also need to change how we encode this. encode. So what we need is, we need double the frequency. Yeah, we shouldn't overcomplicate. Wait, why don't we just write low and high at the frequencies? I mean, everything else is taken care of by analog world. This is way too complicated. Let's do encode bit 3 frequency. Yeah, signal transitions is what we want to do. So we need uint 32 is basically per wave here, frequency ticks per wave, then that's const. Value dark right, we need dark right, then we need oh, interesting. Yes. I hope so. Deck right. So no. Yeah, const uint 64 t get time t0 T0, and then we do like as high of frequency encoding as we can do. So 8T frequency value 4 we can do it more complicated because there will be like a gap because of some stuff that's happening between here. What did it do? Time division? No. If Nicholas, what? No! Just like serial encoding, decoding. We should output what we receive. We should put it via a wire to an UART and try to use the hardware UART to decode it. Oh wow! What is it doing here? What is it doing here? I really want rather this, but it will be probably same at the end. and quarter. No. Yeah, digital encoding. I have too much input in my ear. Yeah, phase. That's what we need. Recalculate that. Phase is T. Nope, we don't need that. I want to simplify that. Yes, it's a mono recorder. FT is okay. If I value I and 1. Okay, this is a physical 1. What I initially did with that frequency spectrogram, I wanted to write 8 frequencies at the same time, and the amplitude would be basically the modulation of the each bit, and there was a 9th frequency for the clock, so we would have like a perfect clock for each bit, but apparently the quality of our encoding and decoding, this is what we tried before, is running a DFT or whatever frequency decoding, and it wasn't like clean enough to retrieve even like 2 bits from the stream. If ticks per wave half. Yeah. Shorter than we do deck right. We just do full swing. Full swing here. I think 64 was what I used before. Pressed. Where am I? Here. Sorry. 64 was. 63 is the max amplitude. And now I'm only using 1 and doing the frequency modulation. Else, and then Wait, 2 quad, no. Oh, this is so stupid. Yes. We took like, that was this last stream. It took us ages to find out that we should take musical notes. And they're not like it was on the spectrogram it was alright, but it fell apart on doing higher encoding rates, and I don't know, somehow it wasn't good enough. Maybe I have to try again, just throw away everything and start new code. Maybe I can do FFT on the fly and then find, like, if there's a deviation, find the frequencies. Alright, where was I? I need to... No, I will just divide it here. Get time and I divide by ticks per wave, and then let's do that. Okay. FFT, yes, on this basic MCU should be doable. Okay, there is a 1. In that case, oh, this is AC. You know what? That's not a bad idea trying to store DC. If we do it right, but then we need to have like the bits flip as well, like in USB. So you need to shuffle if the DC offset is too long, like, so what is it at USB? Yeah, but USB is doing the same. If you have like, I think, what was it, 12 consecutive zeros, it would just flip. Yeah, it's AC coupled, but it's, if we store it really fast, it's probably like a slope, a clean slope, so not many bits that we could store there. Maybe 2 different values, and then you need to flip each. That's actually DC things could be working. So let's see. We need something like this is, oh no. Do it like that. So imagine this is our 0 volts, and what AC does is basically it needs to swing around that. If you have a long long DC value, it will basically be evened out by the AC coupling. But if we store, like, let's say a high, this is like 1, this is 1, this is 0, this is 1, 1, 1. The problem is we could lose sync here. So there is another 0. So what happens on USB, for example, is that whenever we count, okay, there have been 2 rise time is limited. Alright, I mean, you just need to center it here. Or the frequency has to be low enough. Anyways, okay, let's assume it's like a curve, like that. Here you have 1, like that. And then you would have like, so if you have like two, 3 ones, if you have then like no transition for like 2 or like 3 bits or whatever, then you flip everything. And on the receiving side, you need to maintain that. Manchester? Is this Manchester? You can throw all the names at me. Manchester encoding 00 each clock, you flip the polarity. No, because if you have like 1 0 1 1, then you wouldn't want to flip. You would have always like a flat line. You need to maintain it, like how many transitions you had, like in the consecutive bits. Like if you have no transition for 3 consecutive bits, or USB is a 12 or 11 or whatever, then you do an artificial transition. And then you maintain like, oh yeah, I have an X or that or whatever. And that's maintained by the receiving side as well. I think that might be also on HDMI, like TMDS signal are the same. Flipping? No, it's not. What if you flip each clock? If you have like this signal, if you flip like each clock and you have like this signal, you would have like a constant DC that doesn't cut it. You need to do it like in logic. There must be some logic to maintain how many transitions, because the signal could be varying. It's not like for the clock it would be alright. What is this Euro signal? Oh, interesting. Okay, so we have the frequencies. Look what frequencies we picked last time. I show you the frequencies here. They are quite lower, but also the distance is almost like 80 hertz. Here we have also like 80 hertz distance. So this was similar what we picked. Now let me finish my code. We want some to see that working. No, yeah, we want to see ticks. Wait, no. Transition, that would be yeah, that's the phase. we can do basically one times 2. Ticks per wave 4. Okay, so we have okay, Chris, gotcha. But let me finish that. I have you in my ear, so I need to concentrate for a second. Okay, I think this will be what I want. Get time. It's also P while no do not get time. We can do 64t. So t, that's the starting time, and do while t I need ticks per wave. Let's do it then. Seriously? Okay. Okay then. Ticks per wave, we have quarter of the frequency. If it's a 1, we can do the bit here. So if bit deck right, wait, oh, we don't do that. Times, okay, so the doubles the frequency. That should be it. Now we need to just put it there. And do this. No. Yes, for 0, double the frequency. What is 1200? Can do whatever we want. We just need to maintain the transitions. Wow, deck right? Oh, we are too far up there. Damn it. Okay. Wait, what was that? Oh. Void. And we can keep the sync if we want to send more data. Okay, but for now we're just sending 1 byte each single byte here. Okay, I want to see what it does. So connect. We can test it with a different frequency that's and also a different count. Multiple passes per record test. All right. What? There is an error again. Wait, huh? Why did it play? I'm implementing what the C64 did right now. We are counting the zero transitions now. Yes. Snuff, got it! Yes! Zero crossings. Easy peasy. Double the crossings, it's a 0. We just need to synchronize. A sync signal should be even lower then. So we know, oh, that was very slow. That must be the sync signal. And then starting to... the start of a packet maybe. I don't know. What is an identifier? Alright. There is a bug. What bug is that, my friends? I'm writing encode 3 bits. Okay, time. Oh yeah. Ticks per wave. Now we need to T0 and that's not const anymore. Okay, I just add another wavelength to that. Ticks per wave. This is actually is it stupid? No, it's not. That's alright. Guess it's alright. Yeah, I would do like smaller packets in less than a second to find a sync signal, identify the packets, small packets with like, I don't know, maybe 64 bytes or whatever, or 64 bits, and so it would be like 2 bits for the sync if there is like only half the wavelength, so that costs like 2 bits, and then we know exactly the starting point of a signal, and can perform whatever. So whenever we listen in somewhere, we wait for maybe half a second, whatever, to find the starting point of a new packet. But the packets, they need identifiers. Oh, it must be a bigger packet than. Packet 256 packet, 1 byte for packet identifier. Yeah, the I spilled. The overhead will be big. Did you rewind correctly? This device, it wears down. Hey Christian! That didn't work for some reason. Let me check that. Frequency, value, dataset use repeated in twice. Why is it repeated in? Just for error correction? But then oh. How many errors will there be? Wait, uint phase. We are at now T0. Wait, DT. We need that. T0. I'm so terrible, probably tired already. I can ignore that unsupported register. apparently it's easy in hardware because you can use this Schmidt trigger to count the transitions. Now it's recording. Okay. Our test. I mean, if it was developed in one day like I try to do here, then it wouldn't be like so iconic. Okay, let's listen in. Lower frequency. Yeah, it's a complicated schema. Yeah, but like 10 bits per second. Okay. Yeah, we won't be able to see. Yeah. Nah. This is not what I want. Okay. So oops. Or that's good. It has two heads, but only to switch sides. It can switch the sides without flipping the tape. It doesn't use the second one to do anything. It's like a lever. So if you flip the recording direction, it flips to the other head. But it has only one. Let's call it data. So this will keep ticks per wave. This is the frequency. bit. We don't need to, we can just leave it inverted. I don't care. So yeah, that's what's missing. Ah. And we don't need to multiply it, but we can just shift it. 32, we can 63. Okay. Then let's do. Can't put this on the stack. Let's do, what is it? What's the name of the buffer again? Sample buffer. Oh, okay. Sample buffer, not encode, it's just I. Yeah, I have also this one with only one head. But that's good enough. Wait, is it a stereo head? Ah, it can't be. If the can't tell. It's probably not. If it was stereo, that would be cool. Yeah. We tested the frequency last stream or on Monday. 2 drives, nice. Encode packet and then sample box. Alright. Was it encode packet? What was it? Encode packet size. Okay, let's try. I doubt we make the FAT working today. Use it as a data set. That's the end goal. Okay, let's record. Okay, it's running the test. Maybe C64, maybe. Fast forward and play. Ah, that would be cool to try to increase the speed. I want to build from this broken one for example, build a completely new, like take the head, and because the heads are, you can buy a recording head for $12 or something used, or you just buy a complete device for $15 and you get everything what's else inside there. Oh yeah, I got I got this for $15. Included were 2 cassettes of 60 minutes each. So that heads aren't cheap. Yeah, strange, but you can just take it from here. And I don't need like to have like a bad feeling about disabling because that's broken. What's on the cassettes? Yeah, there are recordings. We could listen to those. But I don't want to listen to private recordings from someone here on stream. But we will listen to that. We can identify these are ones, these are zeros, there is a 1, there is a 0. That could work. That could work. You got some private prawn on the VCR. That doesn't look very good. Why doesn't it look very good? It's perfectly fine. Okay, there might be some aliasing, but this is probably from the sampling here. Let me check the sample rate. I bet there is some sampling frequency. Oh, that's limited to... No, there is no phasing. There shouldn't be. No. What? No, there is no... There is... No, this sampling artifacts. Because I'm sampling while sending through the... We can run a read test and send a clean signal back. Okay, so we will do that. Play, decode packet. Let's do that. Not decode packet. We will just... What is 116K? No, we just need 1600. Okay, so yeah, I just sample. I will just sample first and then send you the data. Decode packet. This is stupid because what's the frequency? 1200. Decode ADC. Let's look for. I should find it like that. Decode ADC. Decode. Oh no, this is the second one. This has some stuff that we might need. We just record the samples and ticks per wave. No. Okay. So we want, what will be the sample rate? Let's say 8 times that. So u in sample rate ticks per sample. Oh! Did it listen? It listened to me. It's listening to the microphone. What? Scary. Buffer position. Yeah, so it sounds like window position. Oh, buffer. You witnessed it. I said 8 samples per wave. Crazy girl. Okay, t time minus. No, we don't do that. We don't do. Yeah, we can do buffer position. Blah blah blah, Mr. Freeman, and then we just wait. We just record without any analysis, okay? We just record a short moment in time. Where's the actual? Here. ADC conversion. No. We just do that. Was it 12 bits? Shifted by 4, but there is also, no, we have only like half the voltage from that. Yeah, that will be great. And then we need to wait for another. No, bad boy. Let's do that. While t. Let's do this here. Oh, wait. Time plus ticks per sample. Y get time. Then t ticks per sample. Okay, that should just decode packet, record at a sampling rate. Maybe we should rename it, keep it and rename it. And then we will do the sync stuff. And try to connect. Sorry. Okay. Stop and then retest. I guess that was before it started. We need to wait longer. Let's wait 800 milliseconds. Here you go. That looks perfect. That looks perfect. What are you telling me? This is like maybe increase the sampling frequency. But 800 milliseconds. Look at that. We are almost spot on. Spot on. This is perfect. Delayed 800. This is what we need. It's probably like only a few milliseconds more. So we got that timing right. Let's do... This is the frequency. Starting to look promising. Okay, let's do... Decode ADC. Encode packet. Decode packet. Okay, let's do... Wait. Ticks per sample. Okay, let's do 16 samples. Well, let's go overboard and see actually what happened. If there is like some oddity going on, but I just want to see some samples here. Okay, connect and oops, retake. Oof. Okay, this is an old one. There is a 0, 0, 0, 1, 1, which is clipped. I can lower the volume though, so it wouldn't be clipped here, but it doesn't matter for the transitions. Still looks like there is some aliasing going on, but you can see it's all right. Frequency might be too high. What do you think? Should we do the double the amplitude for the high thing? Oh, let's try that. Increase the amplitude. AGC. Encode packet. But then I can't do the double the... Okay, let me try that. 0, 1. Yeah. Let me try that. That's plus so get an offset. See that? Is it too low? When I try to store it, I center it maybe too low. I should center it higher. Let me try to... No, I can't. This is way too complicated. It how do I decode this? I mean, there is like a swing that looks like it could be a transition, it could not be a transition. It looks like this signal was too low. So center around 60, 33 is a little bit too low. What if I center it around like 40? So I do that plus 8. This is something that would be adjusted in with the bias of the DAC and the ADC. I should have planned in like trim pots there. Okay, let's record a new signal then. The frequency response is not that great anymore on this one here. Maybe I can even increase the amplitude for the high frequency, just to improve that. Okay. Let's see what it looks like. Now let's do the read test. Read test. How about now? Does it look better? But I couldn't tell. Is this a 0 now? It's still swinging back. And then it's lower again. I can't tell. Okay, this looks like a transition here. We have the swing, isn't it? This 1 1 1 and then it flips to 0. Boom. It counts up. So, do we want to introduce the start symbol? Zero line. The 0 line would be this is the 0 line. But what value? Oh, it's going down. Is it encoded or is it in the reading? What? The question? Okay, you know what? Let's just go for it. Let's send packets of a smaller packet. Yeah, it changed, but it looks like it's similar to our playing field there. I'm wondering if we should run an average of the last whatever samples to have the DC offset here. As well, you need to consider that I will pick up the AC signal. Oh yeah, wait a second. We can see. I can run the frequency test. So we will. Frequency change from one bit to the next one. What? The resolution of the frequency analysis won't be great, but we will see two lines. Hopefully. Read ADC and play. Oh, connect first. Oh, we're clipping off the higher frequency. Stop. Wait. Let me check if we are even showing the frequency range, because I think for testing we did a smaller range. Yeah, max frequency. Yeah, that's outside our window. This graph can be off because it's like not the sampling rate might be varying a little, but we see the two main frequencies. Oh, this is the one, my 9 frequency encoding. This is another test. The old tests, you can still see them. This is where we recorded that here. Oh, we can try to store fewer bits or take a lower frequency for our test. Okay, so I will do that because the tape dataset uses a faster playback speed than this microcassette, so we should try maybe a lower frequency here. How about 600? And a recording test. We can also do that. Just send it 10 times. So if we want to find like a packet start, we can do that later. Maybe even send like 100 times, only 16 or whatever. Okay, lower frequency, where is it? what did we say? 600? No, let's do 800. Okay, 600 is really low. No, let's do 600. Let's start low and increase it. Okay, but then we also don't need to send it as often. For debugging purposes, that might be good. Okay. No, it's still recording. It's not a. It's stopping and rewinding automatically when it's done. It's still recording. It's overwriting all our past tests. Oh no! Oh no! I did a mistake. I did a boo boo. Here. 256. Uh-oh. It will never stop. Okay. we have enough data. But all our old tests are gone. I know what else we can change. We are currently recording a square wave. We can try just writing a sinus like our sine table entries. That would maybe disturb it less. Play. Oh yeah. Oh wait. Yeah. I stopped that. Okay, this is much clearer. But what is this one here? Is this a 0? Yeah, it's clipped, I know. Low frequency. But the frequency response is already starting to be bad here. So it's clipped and it's not played back well. But we could Oh, this, I like this. I like this. Peeps, I like it. This is where I see a signal. Now we need to frequency modulation, yes. There is no phase skip. Okay, we leave it like that. Now we add, we send shorter packets. Let's store only 16 bytes, and then okay, 10, 50, 160, 100, 64 times we send that, encode the packet, and then we will I can't remember those shortcuts. Decode ADC. Let's encode it first. Encode packet, and then we will do the following. We will do. No, this is the actual bits, and then we first do the sync. Sync is basically the higher signal isn't clipped. It's like the lower the frequency, plus 40 times. Yeah, let's do that. Sync signal. What? Why not? We need the transitions. We count the 0 transitions, okay? That's what we want to do. Nothing more and nothing less. While get time minus thing. Okay, ticks per wave. That's what we do now is minus T0 is ticks per wave. Is doing that. Then we do back right 64. Let's do it twice. Okay. Let's do that. We need also a silence beforehand. Do we need a silence and then the wave? Okay, let's do a different run here. We need to do... I will do deck right 40, or is it 32? I have no clue. We can do the silence beforehand, then we do the transitions. 64. Preamble, zeros and ones. I want oh, you might be right, but I want to indicate the start of this signal. Zeros and ones. Zeros would be best. Higher frequency, then you can sample the transition. Transition from high to low in that case. Yeah, that's what I'm trying to do, like half the frequency. So we see there is like even fewer transitions, then it must be the sync. Deck right. Okay, let me try this. Oh wait, sorry. Okay. How do I find the start of a packet? Best method, simplest method wins. There is silence, and then like all of a sudden it moves downwards, and I know, oh, there is something. So cool. The suggestions are, yeah, QAM, and that's what ChatGPT said I shouldn't do, because the variation of this play speed. I wanted to use initial. I can show it to you. Even it's still in one of my ChatGPT windows. It said, "Oh, don't use QAM. The tape isn't suitable for that because the playback speed is varying too much." So it suggested different methods, and I have even like an implementation completely done by AI, which uses yeah. We can check the implementation that actually came from what was it, Gemini, or was it ChatGPT? I think it was Gemini. Let me check. CDC tape, that might be it. No, wait, huh? No. Why is it still recording? Oh, did I mess up again? Why is it taking so long? Okay, I should do like 20 minutes. It's overwriting the complete tape now. Start and pro and just not. Yeah, that's what I just did. Maybe we can see it. Huh? All right. There is too much silence, I would say. Something's off in my... Encode back, let me check. Huh? I don't... Yes, I hope so. Know if it's blocked or not. Yeah. Carrier amplitude, carrier frequency, carrier phase, PSK phase, frequency A, carrier amplitude phase. Yeah, software defined radio. Somehow. Oh, I maybe pressed record, not rec test or something. They pressed the wrong button. Yeah, I did. Okay. Here. No, that's in the middle of the packet. It's too late. Damn it. It's not. Ah. Watermelon melon. No, it's, I don't know, it's in an odd state. I need to rewind in the right direction. Because I press too often, it switches the directions on play. Let's play and listen. Okay. Oh no, this is our low frequency packet start. I don't like that. Or is this like, yeah, this is the silence. Yeah. Let's do silence for 8 cycles. You mean it will swing in 2 cycles of sync and 8 cycles of silence. We can also lower the sampling rate, I believe. Okay. Okay, that was the test. That was quick. I should play more of that. Okay. Oh, you can't see it. It's on the left side of this window. Yeah, the lower frequency doesn't work. That looks like maybe the clipping is bouncing back. That looks like the clipped, and then we have ones, zeros, because that starts to count from 0 up. And this is 15. So this is the low frequency. That's completely messed up. The silence is too long. I guess we can keep it shorter, like 4. And then the amplitude of the low frequency, we do it 20 and 44. So lower frequency, lower amplitude, 20 and 44. Oh, I see also a thing. I should also transfer function. we're using 40 here. Let's do 32 again. No, plus 8, 40. Okay, maybe we should use 40 here as well. But I don't think the bias matters at this frequency. What I should do after each bit is send it back to 32. Okay, and we need longer test phase, more repetitions. Let's do only 8 and let's do 64 repetitions. Let's go. I'm hungry, peeps. What's going on? It's almost 12 o'clock. Oh no, you wanted to see something decoded. I don't know if I can make it today. What? Damn it. I really don't want to go away next week. I want to stay here and play with my toys. But I think the sailboat will be alright. Okay. Record tests. Okay. Didn't rewind. Okay, how does it sound? Short packets. Yeah, I can see the wave isn't nice. Ah. Oh, come on. I make it even shorter. Look at this. Bigger scope, yeah. It doesn't look good at all. This low frequency, no good. Might be. Okay, you know what? We write only 4 bytes now. All right. Or you know what? Let's encode just higher frequency, 800. Blame Canada. What? Slightly higher frequency, so the lower one will be also synced up. Otherwise, we just record silence and then do a preamble of 2 zeros, 2 ones or something, or 3 ones. Oh, this is so much fun. Oh, and I need to go away for a week. How should I can't take this with me. This is so delicate. This will break. Yeah, but we saw that was looking not that great. I would try to go higher. We had the last time we were at 1200 when you said it wasn't looking. I'm going to Berlin. Going to Berlin to help a friend put a sailboat into the Baltic Sea. So we will be going, I don't know, the canals to Stettin. I can show you the boat even. Where is it? Do I have the boat somewhere? No, I closed the window. The browser window with the boat names. Oh, maybe I have an email with the actual boat. No, it's not a speedboat. It's unfortunately a sailing boat that is very, very slow. Why did the record test didn't work that well? Oh, now it's working. Okay. What's going on? Why was it going the wrong direction? Did I fast forward by accident? Oh no, it has a built-in motor. It's actually a boat that you could use for crossing the Atlantic or something. Okay. Here it is. Ja, hochseetauglich. Ah. Wait, is this like 1, 1? What this? Scrambled eggs. I just remove it. Yeah. Decode backward. Okay, peeps, I'm almost done for today. I'm really tired. I will try to... Yeah, let's leave the silence in. And... Oh, come on. Stupid thing. Okay. Leave the silence in. We want also... One, two, three, four. Yeah, we would need like some better examples here. So let's put an example. Ah. We want some ones and some zeros here. Or let's do B like that. Then we want maybe two ones, two zeros each. And 4 ones, 4 zeros. And I don't know. All ones. Oops. Just for a test. Alright, Z80, good night. I'll be ending the stream in a few minutes as well. Just want to run a test and then I'm so tired and hungry already that I can't continue here anymore. Okay, rewind. Yeah. 4 hours of streaming for today is good enough. That was a quick test. That sounds like a SID tune. Interesting. So we get 0, high, low. Oh wow. This is already I can't tell which one is which. This somehow must be already a peak. No, is it? We have 0, 1, 0, 1. So where's the 1 here? This is the 0. This must be the 1. I take a screenshot and then we will put it there. We have here we have a duration of, this is how one signal is. That's smart. Okay, this is 1. I want to move it, stupid thing. Okay, so where does it start? Oh yeah, there are 4 transitions here. So this is 1, this is 0. Then we have, oh interesting, that goes right up. It's very fast. So here, and we have 4 transitions. Oh, this will be hard to decode. That really doesn't look like a clean signal. And we see some clipping already here. I like the other signal more, the lower frequency, the 600 or what it was. 600 bits per second. Oh no! Doesn't sound good to me, but it's better than nothing. Yeah. And then you have like CRC and whatnot. Oh no. ASCII art. Yeah. You can see that here. Here, that's clear. Once, and then whoop, 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 whoop. Some ones, some zeros, I couldn't tell which one is which. The sync here. Yeah. That's alright. I mean, 75 characters, we can load something. That's one segment in 8 seconds. Oh no. No, 60 minutes. We have 60-minute tape, but we are running it at double speed, so it's only half an hour. It will certainly run a lot of. We can store everything, but we need to be patient. All right, peeps. I keep you updated. I hope I don't know if there will be a stream next weekend. More likely weekend, or most probably Monday in a week. Thank you for the follow, random person. Yeah, my first one was 56k. I have no clue how they did it. Yeah, it never reached that. Most of the time it was only 33 or 28. Oh, Sonic! Yeah, you were early to all the stuff. I wasn't. I had like to work hard for that in my free time as a student to get any hardware there. No, you're not much older than me. All right, here we go. Thank you very much. It was a blast. I think we are. We are close. I would say we are close to having something that might be able to be decoded. I'm wondering how we can synchronize it. I will read some stuff, try some stuff, and I see you in about a week. I keep you updated. You can check my Discord, the live channel on my Discord, if when there will be something. Otherwise, just subscribe or follow or whatever to be. Bye bye everyone. Good night everyone. It was a blast. Bye 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 bye.